Hi everyone, welcome to the 14th day of the DSA Carnival. Today we'll be covering this is the second day of the session graphs. And our educator for today is Mr. Waqar Ahmad. He is a five-star coder at CodeChef and currently a power programmer at Infosys, also the owner of the popular YouTube channel CodeNcode. My name is Jyoti and I'll be your host for today. I am a student at DY Patil International University. Over to you, sir.
From here. Thank you for the beautiful introduction. So, guys, this is my second lecture on this boot camp. So, most of you might already know me. So, in this lecture, let's see what we are going to cover. Okay. So, first, let's start what we are going to cover in this lecture. So, let me share my screen real quick. Okay. So, is it now? It should be visible. So, in today's lecture, we'll be learning these graph algorithms. First, we'll be learning about the Kruskal algorithm for MST, that is minimum spanning tree. And then we'll moving on for Dijkstra's algorithm for triple SP, that is single source shortest path. We'll apply Dijkstra's algorithm to find shortest distance to every other node from a given source node. Then we'll see what are the shortcomings of Dijkstra's algorithm and why we need Bellman-Ford algorithm. And then we'll move on to learn Bellman-Ford algorithm. And it does the same thing, but there is some shortcoming in the Dijkstra's algorithm which we'll be able to overcome using Bellman-Ford algorithm. And then finally, we'll move on to Floyd-Warshall algorithm for all pairs shortest path. That means for a given graph, you have to find out the shortest path between every pair of the node. Okay, so these are the topics that we'll be covering in this lecture. So let's get started. I really hope I'm able to cover all of this because we only have 1.5 hours, and these are four very important algorithms. So let's get started with Kruskal's algorithm. So Kruskal's algorithm, as you might already know, is used to find out spanning tree. Minimum or maximum depends upon your problem statement. You can calculate minimum spanning tree or maximum spanning tree using Kruskal's algorithm. First, let me just check whether am I even audible or not. So, guys, am I audible? Hi to all of you guys. Just a little confirmation whether I'm audible or not. Yeah. Okay. Harshil, thank you for confirmation. So Kruskal algorithm, sorry for the noises. Kruskal's algorithm can be used to find minimum or maximum spanning tree. So you are given a graph, and then you have to find a tree such that the sum of the weight on the edges is minimum or maximum in the case if you want to calculate maximum spanning tree. What is a spanning tree first of all? So let me just bring up my pen tab, just a second. So first let me tell you what is a spanning tree, right? Because if we don't know what is spanning tree, how we'll be able to learn what is minimum or maximum spanning tree. So just a second while I set my board up. Okay, so sharing screen again. Okay. So what? Let's see first what is spanning tree. Some of you might already know what is spanning tree. So, but still, okay. So suppose you are given some graph. Sorry. So a spanning tree is a tree which you get after removing certain edges of the original graph in such a way that the graph is still connected. This is important. the graph must be connected, okay, even after removing the edges. So if there are n number of nodes, then there will be n minus 1 edges only. Okay, for a graph to be connected or to be a tree, there are n minus 1 edges required. For example, from here you can actually remove this edge, just an example, and this edge. So you see there are 1 2 3 4 5 nodes and we have only 4 edges. So a spanning tree is a tree which you will get after removing certain edges from the graph. Okay, so this is the spanning tree. So the minimum spanning tree will be, let's just go back. So suppose if these were having certain values like this, 2, that is 2. Okay, we try to 2, 2, 5, 7, 8, 3, 4. Okay, so you have, this is the given graph which is a weighted graph, and this is 7. Sometimes I confuse myself with 7 and 4. Okay, this is 7. Ah, sorry, this is 7. So you have to remove edges in such a way that the spanning tree you get is having the sum of the edges minimum. Okay, so how we do that? Of course, we'll apply Kruskal's algorithm. So what Kruskal's algorithm says is that, let me just remove and create some extra space. Oh. So what Kruskal's algorithm says that, this is what is, oh sorry, I don't usually work with this. So this is node, let's say A, this is node B, this is C, this is D, and this is E. Okay, so A, B, C, D, and E. So what it says is that to get the minimum spanning tree, first of all, get the list of all of the edges. So we have A, B. A is connected to B with 2. A is connected to E with 4 cost. This is 4. And then E is connected to D with cost 4 again. B is connected to D with cost 7, and then B is connected to C with cost 3, and D is connected to C with cost A. So what it says is that take all of the edges and then sort them uh, by order of their weights. Okay, so this will be the first edge, then we have this, then we have this. Oh, sorry, first we have, this is the minimum, then this is the second number, this is third, this is fourth, this is fifth, and this is sixth. This is the order of their sorting. Okay, so let's separate them. This is order and this is edge, these are edges, and this is their sorted order. Okay, so what it says that first of all sort all of them, all of the edges, and then one by one connect, take one by one edges in the sorted order and see if these two nodes are already connected or not. So this is how we start. This is A, this is E. Initially there is no connection. Okay, D, C, B. Yeah, these are the 5 nodes. Okay, so let's keep B here. So now first edge is AB. Okay, AB with cost 2. So are A and B connected? The answer is no. So you can connect them and your result will become 2. Cost of the MST, that is your result, for now is 2, right? Initially it was 0. So now we have added this edge. Okay, so this is taken care of. Now that second number edge is this, BC. Are B and C connected? The answer is no. So connect them. The cost is 3, so it will be incremented by 3. Okay, so these two are taken care of. The next edge is this AE, that is 4. Okay, so are A and E connected? The answer is no. A and E are not connected, so connect them. Sorry. So simply connect them, A and E, and the cost of A and E is actually 4. Okay, so this is the cost of your MST till now. Then the next AE we have taken care of. Now we have fourth number edge ED, that is of length 4. Now E and D are not connected, so connect them and add 4 again because it has cost 4. So ED is connected. Now there is an edge at Order 5 is BD. Are B and D connected? So as you can see, yes, B and D are connected actually, right? There is a path from B to D. So we can simply discard this. We don't need this. Now D and C. Now D and C are already connected, so we discard this as well. So the cost of the minimum MST will be 2 and 3, 5 and 9, 14. Okay, so this is how you calculate your MST. So what you will do, take the edge list, sort them, and one by one take the edges and check whether these two nodes are connected or not. If they are not connected, this edge needs to be in your MST, and hence add this one in the MST and then update the result by their weight. Okay, and if they are already connected, simply discard them. We don't need them. So as simple as that. So is there any question regarding this? If not, we'll go for practical implementation. I'll just show you an example with the C++ implementation. So if there is no question, please let me know. If there is any doubt, please let me know so that we can further proceed. I'll wait for your responses for like, sorry, I'll wait for 2 minutes for the responses. Okay. You guys can post your responses in the comment section. Uh, yes, I am for now not sharing the screen actually. Okay, let me just share the screen. There is no problem with that. Okay, so Harshil says there are no doubts. Okay, so I'll just wait 1 more minute. Okay, at least 2 minutes should I should wait. So 6:13 we will continue. Okay, so most likely we do not have any doubt here. So let's continue. Let's go for the practical implementation here. So here you see, this is the Kruskal's algorithm, and let me increase the font size. It should be visible clearly. Okay. So what we are going to do here, you see, we are reading n and m, which represents number of nodes, and m represents number of edges. Okay. So what we are going to do, you might know from here, you see, we needed to check whether these two nodes are already connected or not. So to check that, what we are going to do, we are going to use disjoint set. In the previous lecture, graph theory, graph part 1, you might have studied DSU, right? Disjoint set union. So that is exactly what I'm using here, DSU. If you are not aware of that, I have covered this. I have a separate course on DSU on my channel, so you can go ahead and learn that. So we are using DSU to check whether the two nodes are actually connected or not. So this is to store the parent information of each node uh, to carry out the DSU operations. Okay, this is the edge list, and edge is nothing but a structure with three fields U, V, and W. U and V represent node, and W is the weight of the edge. Okay, so what we are doing, we are reading n and m, number of nodes, number of edges, and this is a for loop that runs from 1 to n. Okay, so for each of the node, I'm setting it to be -1. That represents each node is parent of itself in the disjoint set. Okay. After that, we have m edges, so running a loop from 1 to m, and each time reading edges from, there is an edge from u to v, and weight of this edge is w. Okay. After that, you need to sort the edge list, right? Because of course, as explained earlier, we need to sort them, and this is a comparator operator function that I'm using. So I'm sorting them by W, that is their weight. So basically this will sort the edge list based on their weights, and now they'll be arranged in lower to higher weight. Okay, and that is exactly how we have to process. If you are thinking about to calculate maximum spanning tree, what you can do, you can sort it in the reverse order actually. First you need to have the edge with the maximum weight, and then lower and lower and so on. Okay, so this is the cost of the minimum spanning tree, that is MST, and then there are m edges. We will process them one by one. Okay, so this is VWU. We are checking whether parent of v is equal to parent of u or not. In this join set, this is the way to check whether these two belong to the same set or not. If it is not, then what we'll do, we'll of course increment the minimum spanning tree cost by w, and we'll merge u and v, right? And I'm also printing the edge so that you can see what edges are being added. Okay, and finally you can print the minimum cost. And if you see how find and merge are working, merge, I'm not using union by rank. You might have studied union by rank in the previous lecture, graph 1, because this is one of the optimization technique of DSU, right? And this is a simple find function of DSU where I'm using path compression to optimization to optimize the code, right? So if I show you, if we run this example test case, hopefully we don't get any error. So we need to tell number of nodes and number of edges. So we have 5 number of nodes and 6 edges. Okay, so one is connected to 5 with 2, one is connected to 5 with edge cost 2, one is connected to 2 with edge cost 4, 5 is connected to 4, or doesn't matter, 5 is connected to 4 with 1, 4 is connected to 2 with cost 3, 4 is connected to 3 with cost 2, and finally 2 is connected to 3 with cost 1. So here you see, in this, if you sort this, these two will be processed first. So 5 and 4, first of all, what I'm doing, I'm adding the edge 5 4, right? Because this would come first and then this and so on in the sorted order. So these two are not connected, so first we connected these two, and then 2 3, and then 1 5. Okay, because this is the third edge in the sorted order. And then after that we connected 4 and 3. As soon as you connect 4 and 3, this will form this structure, and hence they are all connected. So the next edges we don't need to add. So the MST cost would be 6 only. You can go this way. Okay, so 2 and 1 3, 2 5, and then 6. So this is how your MST, that is minimum spanning tree, works. This is the implementation in C++. And is there anything left to cover? I think no. And here n is defined to be 100. That is, for this example test case, I am assuming that n won't go beyond 100. Okay, so this you can define using the depending upon the constraint of the problem that you are solving. So is there any doubt now? So we have covered the Kruskal's algorithm, how this can be implemented in C++, and how this works, right? So we have covered all of these things. If you have doubt till now, you can ask. We will wait for like 2 or 3 minutes. So we will continue at 6:21. Okay. Oh, good evening, Puneet. So if you have any doubt, please ask. Okay, till then, I mean, your doubts you can ask in the comment section. Okay, if I see any, I'll try to explain, and we'll continue at 6:21. We'll waiting 3 minutes for the responses. Okay, so hmm, everything's correct. 2 more minutes. Okay, Shagib says, I want to be good in graph. Okay, you need to start with the basics of graph algorithm. Usually, even in the hard problems, the algorithm that we are learning are not actually used. I mean, in the contest, if you are participating in like Div 2 or Div 3 contests, these algorithm will hardly be used. It's not like they won't be used, but they will be hardly used because what I've seen in the past contests, they are able to construct problems of like D and E difficulties using only BFS and DFS. They will appear like Kruskal's algorithm, Dijkstra's algorithm. These will appear, but not as frequently. So you want to be good in graph algorithm, that you should start with BFS and DFS. Practice problems of these two algorithms, BFS and DFS, and then move on for other algorithms like we are learning. And DSU also learn DSU because that is easy to learn. And once you have, of course, as many algorithm, it is good to learn as many algorithm as possible. Okay, so start with DFS and BFS, practice problems related to them. As simple as that. The more you practice, the better you become. Even if you think about it, DFS is used in even the advanced algorithms like HLD, that is heavy light composition, which is really hard. I mean, it is actually a hard algorithm. And there is central decomposition, again DFS will be used. DP on tree, again DFS will be used. So there are many algorithms where DFS will be used. Okay, and so that's why start with DFS and BFS. Learn these two, which are very easy to learn, and then practice as much as possible. So I see no comments. Yes, learning is a different thing. As I said, it is easy, but uh, if you know an algorithm, uh, is it guaranteed that you will be able to solve every problem of that algorithm? For example, if there are like 100 problems with that algorithm, like DFS, for example, if there are 100 problems, can you be 100% sure that you will be able to solve all of those 100 problems using DFS because you know DFS? The answer is actually no. It's for everyone, even for greatest like Gennady or Eric, or even for those guys. That's why it is very important to practice. The more variety of problems you practice, the better you will become. So that is why I'm suggesting you to go ahead, learn these things, as you are telling me that you have already learned these things. So the only thing left for you to do is practice. There are many good problems on Spoj available. You can start with there, or on Code Forces you can find good quality questions. So you can learn DFS from Code Forces, you can practice DFS from Code Forces, and for BFS you can go and start from Spoj. Okay, so we don't have any doubts in the Kruskal algorithm. So let's continue for the other algorithm, that is Dijkstra's algorithm. Okay. Am I sharing my screen? Let me see. Yeah, screen is being shared. Here. So now let's go for Dijkstra's algorithm, what it does. So Dijkstra's algorithm is used to calculate single source shortest path. Okay. So suppose you want to find out shortest distance between two nodes, say A and B, then you can apply Dijkstra's algorithm. But in the process of that, you end up calculating distance of every other node, shortest distance of every other node from source as well. And there is a reason for that. Unfortunately, because the time doesn't permit me, we can't go for the proofs. Yeah, there are two things you guys always learn when you are going for any technique or algorithm. There are two things. First, how this works, how Kruskal's algorithm or Dijkstra's algorithm or any other algorithm works. First thing. Second, why this works. That the second thing is as much important. It is as much important as the first thing, that why this work, the proof of correctness. Okay, that is just as important. So when you go and learn about this, the proof of correctness of Dijkstra's algorithm, you will learn that why we are end up getting calculating shortest distance from source to every other node. So sorry. So so Dijkstra's algorithm basically can calculate shortest distance from a source node to every other node in the graph, given that the graph does not contain a negative edge cycle, or sorry, a negative cycle, right? Negative edge cycle, and that is a problem. For example, if all of these were negative, for example, -3, -3, -1, so this cycle will have uh, the total weight as -3, -3, -1, that is -7, right? If this is negative and the rest two are positive, it would become +1, right? -3 -3 +1, +3 and +1 would become +1, right? So that won't be a problem. But now if we have minus minus and minus, or even minus minus, so overall cost will be negative. If there is a cycle in which we have overall negative cost, then this will create problem for Dijkstra's algorithm, and in that case Dijkstra's algorithm is not able to calculate actual shortest path uh, to every other one, right? And that is why we use Bellman-Ford algorithm to find out whether negative weight cycle exists or not. So we need to make sure when you are going for Dijkstra's algorithm, make sure that your graph doesn't contain any negative cycle. Okay. So first of all, Dijkstra's algorithm can be used to calculate single source shortest path. That is, from a single source, you can calculate distance of every other node, the shortest distance to every other node. How? Let's see. So let's go back to this. Let's take an example, and let me tell you how this is done. Okay, let's first remove all of this. Let's remove these as well. So let's take an example of this graph itself. 1524. We have node 1, we have node 5, we have 423. 4, we have 2, we have 3. Okay, this is node 3. And now it is connected like this. This is connected like this, this is connected this, and this is connected this. I think this is the structure. Yeah. And then 213. So we have 213, and then we have 413. 4, again 1 and 3. So this is the graph. Let's make 3 more readable. So this is the input graph, and now you have to calculate shortest distance to every other node from source node, and let's say source node is node 1. Okay, so shortest distance of every other node from node 1. So how we'll calculate that? See, so what we'll do, we'll uh, see, taking from the source node, what we'll do, we'll create a set. You can use either set or a priority queue. Okay, because each time priority queue, what we need in the priority queue or in the set, we will have a lot of data that we'll be storing. And then each time what we have to do, we have to process the node which we have found till now and is actually having the lowest distance from the source node. So suppose this is the distance array and I only have 5 nodes, so I won't be going for, okay, 1 2 3 4 5. So what we know is that source node is at distance 0 from itself. So we'll be inserting a pair in the set or a priority queue, whatever you want to use. Okay, we'll be inserting a pair. And what information does that pair store? It will store distance and then node itself. Okay, so node 1, which is the source node, is actually at distance 0 from itself, right? Because node 1 is at distance 0 from itself, right? So this is what you have inserted into the set. After that, we'll process the set or priority queue till the point where there is nothing left in the priority queue or the set. So first of all, what you will do, you will take out the node which is having this minimum distance till now. Till now we have only found this node. We have inserted this. We already know the distance of this, and that's why we have inserted this in the set. Okay. So this is having 0 distance. So let's remove this from the set, and it is having distance 0 from the source node. Now we need to process node 1, which is having weight 0. Oh, sorry, which is having distance. The node that we are processing is 1, and its distance is 0. Okay, from the source node. Now process this node and see whether we can minimize the distance of every other node. Just let me do this. Okay. So yeah, one thing I forgot to tell you, this is the distance array. Initialize the source node with 0 and the rest with infinity. Okay. Infinity can be used to distinguish between the reachable or non-reachable nodes. For example, there can be a 6 node which is there and there is no way to reach from source node to this. And once you set the distance of node 6 to infinity, that means node 6 is actually not reachable. Okay, so infinity can be a very huge number which cannot be answered to any node. Okay, distance of any node. So now we are going to process node 1. So what are the nodes directly connected to node 1? Node 5. So if we go to node 5 through node 1, the distance of node 5 would become 0, which was original distance of node 1, plus the edge weight, which is 2. So we can reach node 5 using this edge with distance 0 plus 2, that is 2. Is 2 smaller than the current distance of 5? Of course it is smaller, so we will update distance of node 5 to be 2. Okay, so here, oh, this is very small. Here we'll have 2. So see what happened. Now we are processing node 1. Okay, and we have removed this. Let me remove this from the set or priority queue, whatever you are using. Now we are processing node 1, and node 1 is connected to 5, so we'll see whether we can reduce distance of node 5. Initially the, oh, sorry, my bad. I need to actually update node 5, not node 2. So this is still infinity, this is 2. So what we did, initially it was infinity, so we saw, okay, using node 1 and this edge, because from node 1 I can use this edge to reach 5, right? So using this edge, can I reduce the distance of node 5? Initial distance of node 5 was infinity, and using this edge you can reach node 5 in 0, which is this, plus 2, which is edge weight 2, right, in 2 units of distance. So 2 is smaller than infinity, so you can update it. Once you update it, you see whether, of course when you update it, you simply put this, that is 2 comma 5, in your priority queue or set, whatever you call it, in that. Okay, so now we inserted 2 5 because node 5 was updated. Okay, and it is possible, before inserting we need to check whether 5 already exists in the set or not. So for now it was not existing, that's why I didn't check that. Okay, so the other edge that is directly connected to node 1 is this. So can we reduce the distance of node 2? Well, initial distance of node 2 is infinity, and we can reach node 2 using this edge in 0 plus 4. This is 0. So clearly 4 is smaller than infinity, so we will again update node distance of node 2. It would become 4. Okay, and since we have updated it, so we will also insert 4 comma 2. Again, these are nodes and these are their distances. Okay, now there is any other edge for us to process for node 1? The answer is no. So we have done with node 1. We are done with node 1. Okay, so remove this, remove this, remove this. Okay, so now what we'll do, node 1 have been processed, so we'll go and see whether the set is empty or not. The set is not empty, there are elements in the set. So what you will do, you will take the element which is having the smallest distance. Okay, so this is having the smallest distance, this is having 4, this is having 2, so clearly this is having smaller. Okay, now we are using set because the first element of the set always keeps the elements sorted. Okay, first it will try to sort using first elements. If they are having the same, then it will sort. If they are having the same value, then it will sort using the second value. So currently they are not having equal value, that's why this is here. This is the first element in the set. So what it does, the first element of the set will always have the smallest distance, and that is exactly what we want. At each given point we will process the node which is having currently the smallest distance, and this is having smallest distance. So now let's remove it from here and processes. Node is 5, weight is, distance is 2. Now using node 5 we are going to reduce the distance of the adjacent nodes. So if I go from here to here, I can use this edge to reach node 1, right? So the distance would be distance of node 5 itself plus edge weight of this, which is 2. 2 plus 2, 4. 4 is smaller than 0. The answer is no, so we won't update node 1. Let's go to let's go and see can we update node 4. So for node 4 it will be 2 plus 1, which is 3. Is 3 smaller than infinity? Of course 3 is smaller than infinity. So what we'll do, we are going to update node 4, right? So it will become 3, and of course you will insert 3 comma 4 here, right? And again we check whether 4 was existing or already. The answer is no, 4 was not already existing. The way you can check whether, first you can check whether the value of 4 was infinity or not. If it is already infinity, that means it is not inside the set. Okay, if it is not infinity, that means it may be inside the set. If I have to check whether node 4 exists or not, I will check at 3 comma 4. 3 is the distance and 4 is the node itself. So I'll check whether the pair 3 4 exists or not, and 3 4 exists. Okay, so this way you will check whether it exists in the set or not. So we reduce the distance of node 4 and inserted it into the queue, right? And what are the other nodes directly connected to node 5? Nothing. So node 5 process have been completed. We have processed all of the nodes which can be processed using node 5. The same process will be repeated for every single node. Okay, so remove this because we have processed this. Now this will be processed next, even though this is the set, this is the order that you see, but in the set actually this will be before this pair. Okay, 3 4 will be before 4 2 because it sorts based on the first values actually. Then it goes for second. So now we need to process this because this is having the smallest distance, right? So what you will do, we need to process this. So node is 4 and distance is 3. You, so now we'll see what are the other nodes we can reduce their distances. So again, we can try to do this, but it won't be what we say. We can't reduce distance of this. Why? Because 3 plus 1 will be 4 and distance of 5 is already 2. So smaller. 3 plus 3 is 6. 6 is smaller than 6 is not smaller than, of course, 4. So we can't update the distance of 2 as well. So 3 plus 3 6. 6 and 3 is having infinity. Clearly 6 is smaller than infinity. So what we can do, we can update the distance of 3 with 6. Okay, and now 6 3 will be inserted here sorry, here in the set, right? So you understand what is the process going on. Now after that, we have processed this as well. So please, among these two, clearly this is having the smaller distance, so now we will go to process this 4 2. Okay, node is 2, distance is 4. We are processing this now. So now let's, using 2 we can try to reduce the distance of this and this. So clearly 4 plus 4 is 8, but distance of 1 is already 0, so you can't reduce distance of 1. Let's try to reduce the distance of this, which is directly connected to node 2. So 4 plus 3 is 7. For node 4, 3 is already smaller than 7, so what, we can't do anything. And then 4 plus 1 is 5. Distance of 3 is 6. Clearly 5 is smaller than 6, so what we'll do, we'll update the distance of 3. But before that, we'll see whether this exists in the set or not. Clearly 6 3 exists in the set. So first what you will do, you will go ahead and remove it, right? So let me show you the code where we are doing this so that it is easier to understand, where we are checking the remove code. Okay, so if the distance of the node is not infinity, what we are doing, we are actually finding it using its distance and node itself, right? And then erasing it. So what we are doing here, you see, before, since the distance of 3 is not infinity, that means it already exists in the set, right? So we have to remove it so that new set can be inserted, new pair can be inserted. So we'll go ahead and 5 6 3 6 3 is here, so remove 6 3. Now the new distance of 3 would be 5. How? You already know, because we can use 4 plus this edge 1 to reach node 3, right? We can use this basically. So this is 5, and now we insert 5 3, right? And now work of node 2 is done as well. It is possible that you guys have some doubts here. I'll take all of the doubts at the end after I have explained this. Okay, so now we are done with this. Now there's only one element left, so we'll process this. Node is 3, distance is 5. So using 5 distance, can I reduce the distance of this? 5 plus 3 is 8. Distance of 4 is already smaller than 8. 5 plus 1 is 6. Distance of 2, which is 4, is already smaller than this. So nothing can be done. So remove this from the set. And we are done. Now we'll check whether the set is empty or not. Set is empty. So of course, we will stop. As soon as you stop, this is the minimum distance of each node. Okay. Node 1 is at distance 0. Node 2 has distance 4. You can use this to reach node 2. Node 3 is at distance 5. How you can reach node 3? shortest distance, this is this. Okay, node 4 is having distance only 3, go here and then here. Node 5 is at distance 2, go here. So this is, as you can see, you have found the minimum distance, the shortest distance to every other node. Okay, so let's see if there are any doubts, then we will go for practical implementation. Most probably you guys have some doubts. If not, then we'll move on, okay, for the practical implementation. So okay, so if there is any doubt, please let me know. We'll wait for only 2 minutes. Okay, so it is 6:41, we'll continue at 6:43. So if there is any doubt, please let me know. So Ria says, explain again, but in short. Okay, so what you have to do, we will keep a set or a priority queue. Okay, this will contain the list of all the nodes which we have till now we have found. Okay, and those are unprocessed. So first of all, only node 1 is found. What we assume that only node 1 is found, right? By that we mean that we already know what is the distance of node 1, that will be 0. By the way, node 1 means source node. Okay, so simply insert 0 1, basically source node with 0. Now after that, keep finding out, basically keep taking out all of the these pairs one by one, which is having the minimum distance, and the first value in the pair represents the minimum distance. That's why we are using set, because the first element of the set will contain the pair with the minimum distance. We have to process these nodes in the order of the minimum distance. That's why we are using set. Okay, so this is the at the minimum distance, bring out that the node with the minimum distance, and using the distance of that, that node will act as an intermediate. For example, I already know the minimum distance of node 5, which is 2. So can I use this node and reach other node from here and minimize their distance? Initial distance of all of the other will be infinity. So if you go from here to this node, the distance of this node would be distance of this node already, which is 2, plus this edge, right? Because from here to here you have to go through this edge, and that's why the cost of this will be added. So if d is the distance of current node and w is the edge, then from current node you can reach the next node using d plus w. W is the edge weight, right? So you will check whether d plus w is smaller than the distance already found for node 4 or any other node. Okay, node 4 I'm taking as an example. So that time it was infinity. So clearly 2 plus 1, that is 3. 3 is smaller than infinity. So update it. As soon as you update it, you need to add this into the set also, because this needs to be processed further. And then these whole process will keep on repeating itself. Each node will try to minimize the distance of its adjacent node using the same approach that we have found, or we are using. Okay, so this is what we can explain in the short. Any other doubt or request? Let me just put my laptop on charge. Just give me a minute. Okay. So okay, I don't see any other doubt, and we are already 6:44. So let's go for practical implementation. Okay. So here's the practical implementation of this. We need, clearly again, we are using vector of pair to store the edges. So what we'll do, since this is a weighted graph, so each in the adjacency list will store the node as well as the distance, right? So what we are doing here, we are reading n and m, the number of nodes, number of m, that is number of uh, edges, and then a, b, and w to read input. So n and m, then for each node I'm defining its distance to be infinity, right? This is the pre-processing thing. After that, reading all of the edges a, b, and w. So in the adjacency list of a, insert bw. B represents the node and w represents its weight. And in the adjacency list of b, insert aw, right? This is how you insert weighted graph. After that, we are running Dijkstra, and this is your source node. It can be one, it can be two, it can be any other node. Okay, depending upon the implementation of the problem that you are solving. And after that, and the number of nodes. How many number of nodes are there that I'm passing, because I'm printing that in the Dijkstra function itself. That's why I need an n. After that, what we are doing, we are creating a set. You can do this using priority queue as well. Okay, we'll insert a pair into it. First of all, as I told you, insert the source node, and the distance of source node from itself is 0 clearly. So distance of source node is equals to 0, and insert that. Till the set is not empty, just keep processing them. What you do, you take out the node at the beginning of the source in the set, because that would be the node which is having the minimum distance till now we have found. Okay, bring out that, erase that from the set, because we are processing it, so of course it should be deleted from the set. After that, use the current node. Okay, and after, what we are doing here, in the adjacency list of node u, we are going to process every single node. Basically what we are doing, we are going to process every adjacent node. So e dot first represents the node, e dot second represents the weight. And if the distance of v is actually greater than the distance of current node plus its weight, that is exactly what we just saw, d plus w. Basically we are checking whether distance of v is greater than d plus w. That means we need to update it. But before that, we will check whether distance and v already exists in the set. If it exists, remove it. Okay, because we are going to insert distance of v comma v already, right? So we should not have two instances of it. So we are checking whether it already exists, so we are removing it. After that, we are updating the distance of v, and after that we are inserting in the set so that v can be processed further. And that's how your Dijkstra algorithm work. Okay, and after that, what we are doing, I'm simply printing the distance of every single node. So if I show you, if we run Dijkstra's algorithm for this node, where is it? Yeah, here you see, there are 1 2 3 5 nodes again and 6 edges. One is connected to 5 with node 2. I mean, one is connected to 5 at distance 2. One is connected to 2, distance 4. 5 is connected to 4, oh sorry, with distance 1. And 4 is connected to 3 with distance 3. 4 is connected to 2 with distance 3. So 1 2 3 4, 4 edges I have not included 4 2, right? 4 2 included, 2 3, 2 3 is not included, so 2 is connected to 3 with distance 1. 2 3 is not included, right? So here you see, so distance of each node we have calculated here. Distance of node 1 is 0, then 4 5 3 2, right? Exactly what we have already calculated by hand. So this is how your Dijkstra's algorithm works. So again, this might be a little bit faster because I have to cover 4 advanced algorithms. These are not advanced but medium hard algorithms. Advanced in terms of explanation, okay, and the requirement of understanding and time that you need to give it to understand it. So since these algorithms require little extra time and you need to spend a little more time than this and require extra explanation also, so it is possible that you are not able to understand, but there are many lectures available. Even on my channel I have covered this algorithm as well, so you can go there and learn. Okay, if you are not able to follow this at this pace, unfortunately I cannot reduce the pace because we have to cover the remaining two algorithms as well in only next like 35 minutes. So, and that's why I cannot be mm, more slow than I'm already going. I mean, I cannot reduce the speed. So yeah, if you guys have any doubt till here, please ask. Mm, So till now we have, okay, yeah. If you have any doubt, you can ask. We will wait for like again 2 minutes, and we will resume at 5:52. I mean 6:52. Okay. If you have any doubt or you want me to go through something again, please ask in the comment section. I'll wait for 2 minutes. Okay. So I see no activity. So most likely, you guys don't have any doubt till now. So without wasting any much time, let's go for the next algorithm. That is Bellman-Ford algorithm. Okay. So now we have Bellman-Ford algorithm. As I explained in the previous lecture, I mean in the previous uh, algorithm, that the Dijkstra's algorithm that we just saw has a downfall. And what is this? Let me just explain you with an example. Let's remove all of them. Simply clear all of this. Okay. So now suppose you have node 1, node 2, node 3, and node 3 is connected to node 1. Okay, come on. This is node 3 and node 3 is connected to node 1. Suppose this is 2, this is -4, and this is 1. So what will happen is that node 1 is already at distance 0. What it will do, it will try to minimize the distance of these two nodes. Okay, so from here to here you can reach at distance using distance 2, right? 0 plus 2 is 2, so you can reach, initially it was infinity for both of them. 0 plus 2, that is 2 is smaller than infinity, so we'll update node 2's distance to be 2, right? Now 0 plus 1 is smaller than infinity, so clearly node 3's distance will be updated as well, and it would become 1. Now node 2 will try to do the exact same thing. It will try to minimize, right? So 2 plus 2 is 4. 4 is not smaller than 0. 2 minus 4 is -2. -2 is smaller than 1, right? So it will be updated to -2, right? And now using this, we will try to minimize. See, -2 and -4 is -6. -6 is smaller than 2, so it will reduce the distance here. It would become -6, right? And -2 plus 1 is -1, so distance -1 is smaller than 0, so you will update this as well. So what it will become? It will become -1. Now it will try to minimize distance of this, so -1 plus 2 is only what we say 1, so which is not smaller than -6 clearly, so this will not be updated. Okay, so now since when we updated it to -6, we already inserted into the set. Now we'll use this to minimize, right? -6 minus 4 is actually -10, so this will be updated to -10. So see what is happening. Using this edge, we minimize the distance of this. Now using this, we are minimizing the distance of this. Now using this, will minimize the distance of this, and this will keep going on, and this will not stop. And that is exactly the problem. If you take this path, starting from this, if you do not have any, suppose I do not have any of this, let me just remove their distances for now, right? If I take, if I start from this, I take this path, then from here to here I'll reach at using -1 distance, right? So if I take this one time, it will be at -1 distance. If I take another time, it would be at -2 distance. If I take another time, it would be -3 distance, and the distance will keep on decreasing. Since this cycle that you have is actually a negative cycle, because the overall sum is 2 plus 1 minus 4, that is -1. Overall sum is smaller than that, and that's why Dijkstra may result in infinite loops. Okay, and that will not be able to distinguish, or that won't be able to find out whether there is a negative edge cycle or not, negative weight cycle or not. And that is exactly what we why we go with Bellman-Ford algorithm. Okay, this is able to detect the presence of negative weight cycle. So let's go ahead and take this example: 1 2 3 4 5. Okay, 1 2 3 4 5. So we have node 1, we have node 2, we have node 3, we have node 4, and we have node 5. So let me just draw this: -1 4. Come on, sorry. So here, go this way, -1 this way, 4, -1 4, this is 3, this is 5. So this is 3, this is 5. I need to see the direction 5. Okay, 2 and 1. So this is 2 and this is 1. All of these are directed edges. 2, this is 1, and 2. From here to here, the distance is actually 2. This edge, 5 to 4, is actually -3. Okay, so -3. So this was the graph. Okay, so what we'll do in the Bellman-Ford algorithm is that we'll keep an edge list. Okay, let me show you the implementation in the Bellman-Ford so that you are able to understand it better. What we are going to do, we are going to have an edge list only. Okay, you see, edge is actually again the structure having three fields: UV and W. Or UV, the nodes, there is an edge from V to U, there is an edge from V to U because this is directed. Okay, there is an edge from U to V to U, and it has weight W. After that, what we are doing, we are not doing anything here, we are reading the edges. And after that, you see what I'm doing, I'm only I'm running two nested loop, one from 1 to n minus 1, right? And then the other for each edge in the edge list, basically number of edges. So it is running n into v number of times. So basically what we do, uh, Bellman-Ford says that relax each edge exactly n minus 1 time. Now why is that so? See, the maximum length path in a graph with n nodes can be only of length n. For example, if you see here, sorry, n minus 1. If you see here, the length of the path from node 1 to node 4 will contain n minus 1 edges. So in bamboo type of graph or tree, you want to call it, the distance, the maximum number of edges a shortest path can contain will be actually n minus 1. And that is exactly why we run the loop n minus 1 number of times. And each time we do it, we will try to relax the distance of the other node, right? Starting from UV. Basically, we each time use an edge and relax it. So what does that mean? Let me show you. So this actually goes longer. So I have node 1, and I have node 2, 3, 4, and 5. Let's have a line for each of them so we don't make any mistakes. So see here what will happen. Node 1 is a source node, right? So it is having 0 distance, the rest will have infinity distance. So make an edge list. If I explain this on this example, it is going to take a lot of time. So let's, because what we have to do, we have to relax each edge. Basically, if there are n number of nodes, I will run a loop There are 5 nodes, so I have to run it 4 times into number of edges. So 3, 3, 6, and 8. I have to explain 40 different times, and that is a lot of, work to do, right? And it will only waste up our time. So what we can do, we can actually reduce the number of amount of work, because the only purpose. Okay, sorry. Let's go ahead and explain this, and I'll explain for 2 or 3 processes, and then the rest of the process is exactly the same. The rest of the iteration is exactly the same, so we won't do that. Okay, so create a list of edge. There is from 1 to 2 with -1, from 1 to 3 with 4. I need extra space for this. Okay, there is an edge from 1 to 2 with weight -1. I don't have much space, so 1 to 1 to node 3 with 4, 2 to 3 with 3, and 2 to 4 with 2. Okay, these are the 4 edges. The next 4 edges are from 4 to 2 having distance 1, from 4 to 3 having distance 5, this edge, and then from 2 to 5, have I covered 2 to 5? No. From 2 to 5 distance 2, this edge, and then 5 to 4 -1. Okay, so now what I'll do, iteration 1. Okay, in iteration 1, what you'll do, we will have total n minus 1 iteration. Here you see we are going for the first iteration. Okay, we'll go for first iteration. We'll in the first iteration we'll go through the whole edge list. Then we'll go for next iteration. Then we'll go through the whole edge list. Okay, so now we are going for the first iteration. So let's start from here, 1 to 2. Okay, from there is an edge from 1 to 2 with -1. So distance of 1 plus weight of this edge, is it smaller than the distance of 2? So distance of 1, which is 0, plus this edge, which is -1. So 0, 0 minus 1 is -1. Is it smaller than the distance of node 2? Distance of node 2 is infinity, so clearly it is smaller, right? So it will be updated to -1. 0 minus 1 is -1, because we are relaxing using this edge. Okay, so distance of the first node, because starting from this we will go to this node. Okay, so starting from this, so distance of this, which is 0 right here, and -1 clearly, because you have to go through this edge. So 0 minus 1 is -1. You are reaching node 2, right? The distance of 2, which is let's update it here right away. Clearly -1 is smaller than infinity, so its distance would become -1. Now the next edge is 1 to 3. So distance of 1, which is 0 plus 4, 0 plus 4 is 4. Is 4 smaller than the distance of node 3? Distance of node 3 is infinity, so clearly 4 is smaller than infinity. So update distance of node 3 to be 4. How 4? Because using this edge, distance of 1 plus edge weight, which is 4. So 0 plus 4 is 4. 4 is smaller than infinity, so that's why updated. So 2 to 3, 3. Distance of 2 is -1, and 3 -1 plus 3 is 2, is the distance of, sorry, let me write here, 0. Distance of 2, which is not 0. Distance of 2 plus 3. Distance of 2 is -1 plus 3 is 2. Is 2 smaller than the distance of node 3? Distance of node 3 is 4. Clearly 2 is smaller than 4, so update it. Become 2. Okay, and now next edge, 2, 4, 2. So distance of 2 is -1 again, -1 plus 2. So this would become 1. Is 1 smaller than distance of 4? 1, yes, is smaller than distance of 4. So do this. Update the distance of 4 to be 1. And then next edge is 4 to 1. 4 to 1. So distance of 4 is 1. So 1 plus 1, that is 2. Is 2 smaller than distance of 2? distance 2 is -1, so clearly 2 is not smaller than -1, so ignore this. So distance of 4, which is 1, 1 plus 5, which is 6, 6 smaller than distance of 3, 6 is not smaller than 3, so don't do anything. And then again, distance of 2, which is -1, -1 plus 2, which is 1, is 1 smaller than distance of 5, 1 is smaller than distance of 5 clearly. So what we'll do, we'll update it to be 1. Okay, after that the last edge is 5 4, so distance of 5, which is 1, 1 minus 3, 1 minus 3 actually, 1 minus 3, which is -2, is -2 smaller than the current distance of 4? Yes, -2 smaller than current distance of 4, so it will be updated to -2, right? So this is what relaxation means. Using the first node plus the weight of the edge, try to minimize the distance of the second node, right? And that is exactly what we did. So this is t is equals to 1. Now we have to perform 3 more iteration, and each 3 times we have to go through all of the edges again and again, right? So basically, after the ith iteration, Bellman-Ford algorithm guarantees to find the shortest distance which are having distance less than equals to I. Okay, so that's why we have to go till n minus 1, because the minimum distance between node A to B can have n minus 1 edges. So this was only first iteration. In the second iteration we will do the exact same thing, and that's why I'm not going to do this here, because if we go ahead and do that we will be wasting our time only. So here you see, before I move on to implementation part, let's see if we have any doubt till now. So Chirag says amazing. Thank you, Chirag. So do we have any doubt till now? We'll wait for 2 minutes. It is 7:07. We'll resume at 7:09. Okay. So if you have any doubt, please ask in the comment section. So mm, okay. So someone asked, 12th May, she got below 60 in 12th, right? Below 60. So product based company milegi yani. So Suman, you go for the job after graduation, not just after 12th. Okay, so you have 4 years for graduation. If you go for graduation, so you have at least 4 years, right? So go try to get a better college, right? There are many. Try to have a college which is good. If you are not, then it's not like it's the end of the life. Just you need to focus on two things. First, your coding skills, like algorithms and data structure, because if you go for any product based companies, the first round they have is the algorithm design round. Like they have contest of around 1 and 1.5 hours. They ask you to solve one or two problems generally. Okay, and it's like going for div 2 contest. So for that contest, if you are not able to go past that first round, you won't be placed in the product based company. So first thing, you have 4 years, so go ahead and learn data structure and algorithm. Spend your time as much as possible, right, to learn data structure and algorithm for preparation of the first round of any product based company. The second thing is, uh, I think they with of course they any interviewer would prefer a guy who have some experience. So in third and the fourth year, try to do some internship. One or two will be enough. I mean, two should be enough. Okay, try to do some internship. Okay, learn some tech. Like if you want to be a backend developer, like learn Django or Spring Boot, or if you want to be a front end engineer, you can learn Angular, Vue.js, and other things like. And if you want to be an Android developer on iOS developer, for Android development you can learn Java and or Kotlin, and make any tech stack you want to work with. Just learn that, make 2 and 3 projects, and after that go to internshala, search for some internships you will find there. Okay, do some internship in your third or fourth year. After this you will have experience, and your profile, your resume will be really so solid that you will be able to get in product based company again. You will get chance to go into product based companies if you get reference, okay, referrals, sorry. So for that you have to of course create your network, go to LinkedIn and create and expand your network. So first of all you need to go to college, okay, think about graduation first. So okay, thank you Chirag. Actually DS and algo is not that important for web development, but you should have the knowledge of what is happening under the hood when you are working. Sorry guys, I think my internet just disconnected. Sorry for that. So Mohit, I mean, the data structure and algorithms are not that important in web development, but you should have basic knowledge of how the things are going under the hood. Okay, you are using set, what, how the things are happening in the set. You are using vector, and what is the advantage or disadvantage of using hash map instead of set, or hash map instead of vector, or so on. Okay, so for that you need to have the knowledge of what is happening, right? So basic data structure and algorithm thing knowledge is very much important, especially the algorithms. Okay, it is I can say actually it is required. Basic algorithms, not the advanced ones. The advanced ones that we are actually learning, uh, it will be hardly used depending upon what job you are doing. Okay, if you are implementing certain map functionalities, then you need to have the knowledge of like single source shortest path and other algorithm. Okay, so but again, to get the job in a good company you need the uh, knowledge of data structure and algorithm to clear the round one, which will be based on data structure and algorithm problems. Okay, so yeah, so I think we don't have any doubt in the Bellman Ford algorithm as well. So let's go ahead and finish this with our last. Okay, yeah, I didn't tell you. So see what is happening is that how you will be able to detect the here is the implementation of this, as easy as this. We are going through all of the edges and checking whether from using node v, using the distance of node v, we can actually minimize distance of u. For that v actually should be reachable, right? It should be reachable, or in other words, its distance should not be infinity. Okay, its distance should not be infinity. Infinity, what we define infinity, infinity is a distance which cannot be a distance of any node ever. Okay, so using the constraint you will be able to define it. Okay, you are able to figure out the, okay, the maximum distance between any two node can be like 1 million. So infinity you can define as 1 million plus 1, or 10 million, whatever you like. So if the distance of v is already not evaluated, infinity means not evaluated till now. Okay, so if it is already not evaluated, you can't use it to minimize the distance of v, so we will simply continue. Otherwise, if the distance of v plus w is smaller than the current distance of u, so we can update the current distance of u. How you'd find out whether this contains any cycle or not? It's easy. Run this n number of times. Okay, if in the nth iteration you are able to minimize, or you are able to minimize the edge, sorry, the distance of any single node, even a single node, that means it contains a negative weight cycle. Because if it was not containing a negative weight cycle. The number of edges, the maximum number of edges two nodes can have in between them in the shortest path, remember, is n minus 1. If you are able to update it till nth time, that means it contains nth edge. That should not be possible, and that means it indicates presence of a negative weight cycle. And that's why if you want to check whether it contains negative weight cycle or not, run the same algorithm nth time. Okay, and if in the nth time we are able to minimize the distance of certain node, it clearly is the sign that it contains a negative weight cycle. Okay, so this was Bellman-Ford algorithm. Now, after Bellman-Ford algorithm, till now we have learned how to find out the shortest path of other node from a single source. Now, Floyd virtual algorithm is actually all pair shortest path algorithm. Again, if you guys are not able to follow and our speed is too fast, unfortunately for every speaker here we have a certain time limit because of sometimes our own reasons, like because of my job and all things, and other reasons as well. So we have to finish all of these things in a very limited time, and that's why we are not able to go as slow as we should. We are keeping the pace optimal. Okay, so if you are not able to understand, we already have these we already have I already have two courses on graph algorithms, where I have explained everything in detail using 3 or 4 different lectures for each concept. Okay, so that and also taking certain problems so that you guys can practice once after you learn those algorithms. Okay, so if you are not able to understand, go through those lecture if you are able to. Okay, if you really want to learn, here our speed is actually optimal as much as we can. So the next algorithm is Floyd-Warshall algorithm. The thing about Floyd-Warshall algorithm is that using this algorithm, you will be able to find out the shortest path between each pair of nodes in the graph. There is not a specified source. For example, Dijkstra or Bellman-Ford uses a single source and then finds the minimum distance to every other node. Here, we need to find the distance of every node to every other node. For example, I need to find the minimum distance between node 3 and 4, or node 3 and 2, node 3 and 1, or 1 and 4, 1 and 2, right? So I need to find the shortest. The question can be find the minimum distance between any two nodes, right? In that case, we need to evaluate the minimum distance, the shortest distance between each pair, and that's where Floyd virtual algorithm comes in. It uses dynamic programming approach. So how this works? So let me just let's clear this and see how Floyd virtual algorithm works. Let's clear all of this. Okay, so I have a fairly simple graph because here we need an n cross n matrix. 1 2 3 4, node 1 2 3, node 4. I think this is how the graph looks. 1 2 3 4. Okay, so now we need a matrix of n cross n size. So let's say this is node 1 2 3 4, node 1 2 3 4. Now what is happening here, I'll explain. Just let me complete this. Okay, so this matrix will keep distance of basically the shortest distance between node I and j. The cell ij will keep the minimum distance from node I and j. Okay, between node I and j. So since the distance between each node to itself is actually 0, so distance between 1 1 2 2 3 3 and 4 4 you can initialize with 0. Okay, now we have edges. 1 is connected to 3, so 1 3 will have distance 2. Okay, and of course 1 3 will have distance 2, and 3 1 will also have distance 2. Why? See, You can reach from 1 to 3 using this, or you can reach from 3 to 1 using this, right? So from 1 to 3 and 3 to 1, we can write these. And same goes for 1 2 and 2 1. 1 2 and 2 1 will have 4 and 4. This as we have covered. This you can initialize at the time you are receiving the input. Okay, you will receive the edge abw. What you can do, you can go, if you call this dp, so dp of ab is equals to w. This is what you can do. And dp of ba is equals to w. This is what you can do. So whatever I'm typing here is actually you can do at the time of taking input, right? So I've taken care of this and this edge. So 2 4 and 4 2 will have 3. The distance between node 2 4 is 3, and the distance between node 4 2 is also 3. It is possible that these are not final answer. We can get a better solution. For example, if this was 13, say, so I have a better path from 2 to 4. For example, this path, right? So we are, even though we are filling these values, it is still possible that we get better solution. Okay, now this 3 4 and 4 3, 3 4 and 4 3 1. Okay, we still have to find the minimum path between 3 2 2 3 1 4 2 3, right? And 1 4 here. So these are the paths, and these paths that you see may actually reduce. So let's go ahead and see what happens in the Floyd-Warshall algorithm. So this is only pre-processing part, where define a DP array or a distance array of n cross n, right? And cell ij represents the shortest path between node I and j. Now what happens here is that what suppose you want to find the shortest path between node AB, okay, node A and dash 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 dash. So there are some intermediate node in the shortest path. Okay, this is generalization. So this is the shortest path between A and B. There will be some intermediate node, right? This is the path. Okay, so what Floyd-Warshall says that there is an intermediate node. Using the intermediate node, you can actually calculate the distance between AB. So the distance between AB, the shortest path between AB, can be broken down into the intermediate node K. So distance of AK plus distance of KB. Make sense? I mean, this is just like the basic observation. So the path, the general path, that is actually A dash 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 B, that goes through certain edges. What you can do, you can take an intermediate node. It can be any node, this or any node. Okay, we don't know what node it will be, but every path you can actually divide in certain AK plus KB path. Okay, basically you can choose an intermediate node, and you that whole path will be divided into AK plus KB. Sorry, and that is exactly what the algorithm of uh, Floyd-Warshall is based on. So for each node, I'll see whether using this as intermediate node, how can I reduce the total path of other node, right? Other pairs. So for each node, we'll see whether this can be a better intermediate node or not. Basically, for each node, just take it and try to make it intermediate node to every other pair. I will do that and show you. Oh, okay, sorry, I should have done this better way. Okay, so first of all, am I audible? Because Azan ho rahi hai, so am I audible? Can anyone confirm? Not getting any confirmation. Yeah. Thank you, Nandini. So I am audible. So how we'll do that? For each node, we'll try to make this an intermediate node. Okay. So what I'll do for node one, let's go ahead for every single. This you will better understand if I write the, because I cannot write pseudocode here. So see, So what you will have a dp or distance array, doesn't matter, of n cross n. Okay. After that, what you'll do, I'm assuming that we have done all of the initialization. Okay. After that, what you'll do, for each node, you'll try to make this as intermediary node. Nodes are starting from 1 to n. I'll see whether node these are all the nodes which we'll use as intermediate. When you see the code, it will become easier. If uh, dp of what we'll do basically inside of this, dp of ij, basically the minimum distance, the shortest path from I to j will be dp of ik, the path from I to k plus the minimum path from k to j. So understandable, what we are doing, we are breaking the path ij in I to k and k to j. Each time we are trying to check whether the ith node or whether the kth node, sorry, is actually the correct intermediate node or not. Before doing this, you need to check if dp of ik is not equals to infinity. Of course, this we should have already been calculated, because here you see the field that you are watching is actually not filled, is filled with infinity. Okay. The fields which are not filled, you can define them by infinity. That means they have not been calculated yet. So first of all, since we are going to utilize ik and kj, ik and kj should not be equal to null, first of all. And the other thing is, let me just create some space, dp of you can use minima. I actually don't need to do this. What I can do, I can do this. Okay, I'll just show you minimum of this or dp of ik itself. You see what we are trying to do, we are trying to find the distance, or basically trying to minimize the distance between I and j using k as the intermediate node. And that's why we are trying to minimize the distance of I. This is not ik, this is ij. This ij we are trying to minimize. Either it will be ij or this, which is smaller than, if it is smaller than distance of ij already found, it won't change. Okay, so this is how the Floyd-Warshall algorithm works. So what it does, for each node, it considers it as the intermediate node. So we break the path from I to j into I to k and k to j. And using this, we see whether it is possible to minimize the path or not. So if I run this example test case, okay. So using node 1, can I minimize the distance of all of them? Let's see. So distance of 1 1 using 1, because internal loop runs from 1 to n and j runs from 1 to n as well. Okay, the overall algorithm takes n cube of time. N is 4 here. Clearly n cube, I won't be able to uh, I won't be able to show all of the examples, so I'm only going for node 1 as intermediate node. For rest, it is the same. So let's try to minimize 1 1, then 1 2, then 1 3, then 1 4. Okay, so 1 1, dp of 1 1, let's initialize all of these to infinity. dp of 1 1 is actually 0. Is it dp of, if we are using this as intermediate node, then we need to find, this is the node below which there is underscore is the intermediate node, plus 1 comma 1. So dp of 1 1 is smaller, or dp of 1 1 plus 1 1. Basically, this is I, this is j. I have broken down this path from I to k. K is 1 in this case, because we are using 1 as the intermediary node. I to k and k to j. So see, I, which is basically 1 1 is 0. So is 0 is smaller or 0 plus 0 is smaller? Clearly 0 plus 0 or 0 are same. So this dp of 1 1 won't be changed. Let's go for 1 2. So dp of 1 2 will be broken into 1 1 plus 1 2, right? Ik and kj. So dp of 1 1 is actually 0 plus 1 2. 1 2 is actually 4. So 0 plus 4 is 4. So path from 1 to 2 would be this. And of course, it becomes 4, and 4 is not smaller than 4. So nothing would happen here as well. Same way, oh, same way we'll try to minimize path 1 3. If you see 1 3, 1 to 1, and then 1 to 3, right? So 1 to 1 is actually 0 plus 1 to 3, you see, is 2. 0 plus 2 is 2. Is 2 smaller than 2? Answer is no. So it won't be changed, right? And the last one is 1 to 1 plus 1 to 4. 1 to 1 is 0 plus 1 to 4 is actually infinity. Actually, we won't be updating this because we won't be able to update it because there is no path we have found till now from 1 to 4, right? We haven't found any path from 1 to 4 till now. That's why it is infinity. And since this is infinity, sorry, since this is infinity, where is that? Where is this? Oh, I have written this as null. It will be infinity. Sorry, and this will be jk, kj. Sorry. So since this is infinity, kj is actually infinity. We won't be minimizing it. Okay. So this won't be updated. 1 4 won't be updated. So 1 1 1 2 1 3 and 1 4 have been updated. Basically, after this, we would have been found all of the paths which are directly connected to 1. After that, we'll go and minimize using we have done like 1 1 1 2 1 3 and 1 4 we are taken care. Now we'll go for uh, 2 1 2 2 2 3 and 2 4, and then same for 3 1 3 2 3 3 3 and 4 and so on. So it will become very messy if I do that. And here the rest is exactly the same that the example I have just given. For each node we will consider this as intermediate node, and what we'll do, we'll try to break the ij path into ik and kj, okay, like this, and try to minimize by this. And this is how your Floyd-Warshall algorithm is supposed to work. You need a better example. There are like 2 3 guys on YouTube who have given better example because of course they have much uh, extra time as compared to what we have for now. So if you are still not able to understand this, this is a pretty straightforward solution. You take every single node as intermediate and take every single pair you can form from the remaining nodes, right? How many pairs you can form? You simply run two loops, and this will represent the total number of pairs you can form. The path between each pair, break it between ik and kj, and simply minimize using that. As simple as that, right? You should be able to understand this. But still, if you want to understand using an example, since my time is already up, you can Google this and you may find a better example. Okay. So yeah, Nandini, thanks for mentioning it. I've updated it. Okay. So yeah, this was all for this lecture. And also, if you guys have last thing, if you do, you guys have any last, what we say, any doubt till now, I mean, about this lecture, or you want to know how you can learn this in a better way, or any other question related to graph theory, general question related to graph or tree algorithms, okay? Any general question. If you have any question, please post it down. I'll wait for like 2 minutes, and then we'll leave, okay? If we have any questions. We'll wait till 7:37. Okay, and then we can finish it. No. Okay, so we don't have any doubts. So I think, Jyoti, we can end the session here.
Right, sir. Thank you for this wonderful and informative session. We're really honored to have you today.
Thank you, Jyoti. Same
Um,
here.
yeah. So now for the winner of yesterday's quiz, it's Himanshu Singh from Motilal Institute of Technology. Congratulations, Himanshu. The link for the practice sessions for today's session are in the description, and the link for the quiz as well is in the description. Please take the quiz before 12 a.m. today and stand a chance to win a T-shirt from Prep Bites. Thank you all for joining us today, and we'll see you all tomorrow.
Thank you, guys, and for being a beautiful audience. Thank you.